One of the major tasks of the cardiovascular system is to deliver enough blood flow through the capillaries to meet the needs of the systemic tissues. And hemodynamic principles are the principles that control this blood flow through the cardiovascular system. These general hemodynamic concepts are flow, pressure, resistance, and compliance. And these principles of physics form the basic mechanism for how blood flows through the vessels to the tissues and for how mean arterial pressure is regulated. We'll look more in detail at each of these principles, and particularly how they're related to each other. But let's start by focusing on this relationship between flow and pressure. So first, remember that mean arterial pressure, which is the driving force for blood flow, is primarily determined by two main factors. And those are cardiac output, which is determined by how much blood the heart pumps per unit time. So this is the flow variable. And then the systemic vascular resistance. So if you increase the flow, or you increase the resistance, it'll ultimately lead to an increase in the mean arterial pressure or the driving force for blood to flow to begin with. And if we rearrange this equation to focus on blood flow, we get what's known as Ohm's law equivalent for the heart. And that general equation is here and now. We can see the major determinants of blood flow Q are pressure and resistance. So based on this relationship, if we want to increase the blood flow to the tissues, we can either increase this pressure or driving force, or we can decrease the resistance. And alternatively, to decrease flow, we can either decrease the pressure or increase the resistance. And as we'll see, the main mechanism for changing blood flow is by changing this resistance variable in the blood vessels, and more specifically by changing the resistance in the arterioles. We can also rearrange Ohm's law so that we look at the factors that lead to changes in pressure as blood flows across the vessel. And based on this rearranged equation, we can see that what leads to a pressure change, or really a pressure drop, is the amount of blood flowing across that vessel and the resistance of those vessels. So this means that the greater the resistance of the vessel, the larger the pressure drop, because more of that driving force has to be used to push the blood across that higher resistance. We can compare the pulmonary and the systemic circulations to get a better idea of how this relationship works. So if we start here looking at the systemic circulation below the dotted line, the pressure that's generated by the left heart is on average this 93 millimeters of mercury, and that's our mean arterial pressure for the systemic circulation. As the blood is taken to all of the organs and tissues of the body, it then flows back across the arteries, arterioles, capillaries, and then back to the right heart through the venules and veins. And as this blood flows, the pressure drops from that 93 millimeters of mercury all the way down to between 1 and 6 millimeters of mercury. So this is a really large drop. So we have a large delta P in the systemic circulation, indicating that the systemic circulation has a pretty high resistance. And if we compare this to the pulmonary circulation, which is up here above the dotted line, in the pulmonary circulation, we start out with a mean arterial pressure of about 15 millimeters of mercury being pumped out from that right heart. And first, you can see we're starting out with a much lower pressure than in the systemic circulation. But not only that, there's also a much smaller pressure drop as the blood flows across the lungs and all the way through that pulmonary circulation down to only 5 millimeters of mercury. So that means that the pulmonary circulation is a low resistance circulation. And remember that in both the systemic and the pulmonary circulation, the Q is constant, and that's because the cardiac output of the left heart is equal to the cardiac output of the right heart. So since we see this difference in the pressure drop and we know that the flow is constant, we know that this must be due to a difference in resistance between the systemic and the pulmonary circulation, with the systemic having a very high resistance, the pulmonary having much lower resistance.